What's up, kids? This is Mr. Carlson, C-Squared Mathematics, and today what we're going to be doing is 6.1, confidence intervals. So we are going to learn what happens when it's not normally distributed. What happens when data from the sample and the population is not necessarily normally distributed like we would like. Okay? So I'm going to skip the bell arc for today, and we're just going to go straight into the notes, and that's probably what it's going to be like for most of the assignment, for most of this week, because I have a lot to talk about, and I don't want to waste time going through the bell work. So let's get started. The essential question: how can I calculate, and how do I calculate confidence intervals and margins of error? So we're going to learn about what those are, the confidence intervals, what margins of errors are, and how they relate necessarily to samples and population parameters. Okay, and then of course there's other things that we need to learn as well, but we're going to get into that later. And we're also going to be using a Desmos calculator, which I'm going to show you in a little bit. So first things first, confidence intervals, what are they? And it all starts with what we call the population parameters. Again, if I know, let's just say I do know the population parameters, like if I know what the standard deviation of the population is, or if I know the mean of the population, then this is perfect. So 6.1, if I know what the population is or the standard deviation, then that means I'm going to use this lesson, all of this math that I'm about to teach you, as follows. So what does that mean? It means we start, first of all, with defining what the population is, and we can actually use what we call a point estimate to find or to estimate the population parameter. So the point estimate is a single value estimate for population parameter. It is the most unbiased estimate of the population parameter. And specifically, what we say is the most unbiased point estimate of the population mean is what we call the sample mean. So the sample mean is really the most unbiased point estimate of the population. You take any given sample, and then that is more than likely going to be a good estimate of the population. Okay, just like what we kind of talked about last week with populations and how they relate to your samples, with the means and the means of the sample means and then the means of the population equaling each other. That's sort of what we're going to be doing today. Now, a statistic is unbiased if it does not overestimate or underestimate the population parameter. Okay, so if X is an unbiased estimate of mu. Now this X should be like an X bar here, and that X should be an awesome X bar. So that means if I take any given sample, it just can't exceed the population. It can't exceed the population mean. Okay? So let's go through a couple examples here. Very, very short, simple examples, actually. So an economics researcher is collecting data about grocery store employees in the county. The data is listed below it's actually not listed below for me. It's listed for you guys, though. Okay, so you guys will have it on your sheet. So just look on your sheet, and it's listed, your note packet. And hours worked by 40 employees from several grocery stores. So we want to find what we call the point estimate. So the point estimate is really just the mean. And what this is your X bar equals, I add, that's what that symbol means, add, sigma. I add all of my X values up and I divide by N. That's what that is. Okay? Oh, shoot. I guess I did have them. So they are shown below. But at any rate, my point estimate is still this. So go ahead and add them all up. What's my point estimate? My point estimate is X bar equals my sigma, or my adding of all of the X's, all over my N, which is my sample size. So when I add all these up, I get 1,184 divided by my sample size of 40 employees. When I do this, what I get is 29.6. So this right here is my sample mean, and it's going to be acting as though it's the population mean. So it's a good point estimate. All right. Let's go through another example. Another random sample of workers worked by 30 grocery store employees in the county is conducted. Assume that the total hours worked is the same as example 1.1. So, what was the total number of hours worked in example 1.1? Well, that was 1,184. But now what I'm going to do is I'm going to change my n value to be 30. So now what does this equal? This equals 39.5. Okay, 39.5. So on average, they worked about 39.5 hours. Okay, even though we don't know what those actual hours are because we're just assuming that the total is the same. So that's the point estimate. Very simple, right? Not too terrible. And we're going to use this point estimate to build what we call the confidence interval. Okay. So before we get to the confidence interval, we need to know what an interval really is. I mean, for real. So what is an interval? Okay, think about it like this. In example 1.1, the probability that the population mean is exactly 29.6 is virtually zero. Like it's freaking impossible. There's no, even though that was our sample mean, there's no way that the population is probably going to be 29.6 exactly. So instead of estimating, so instead of estimating mu, my population mean, to be exactly 29.6 using what we call the point estimate, the sample mean, you can estimate that mu, the population, lies within that interval, a specific interval. But what specific interval? So what you're basically going to do is calculate what we call an interval estimate. And that interval or range of values is used to estimate where the population parameter could lie. So where your actual population mean could actually lie. Okay, because again, it's virtually impossible that my sample mean will equal my population mean. So what we do instead, like what I was saying here, is we calculate an interval estimate to see whether or not it's between these bounds. Okay, and if it's between these bounds, then we can ask how confident are we that this is the case. Okay, so this is what it would look like. Although you can assume that the point estimate in example 1.1 specifically is not equal to the actual population mean, it's probably somewhere close, right? More than likely close. To form an interval estimate, we go on, use what we call the point estimate, 29.6 from example 1.1, as the center of the interval, and then add and subtract what we call a margin of error. For instance, if the margin of error is 2.1, then the interval estimate would be given by 29.6 plus or minus 2.1, or 27.5, and then our mu, our population mean, and then 31.7. So where did I get these numbers? Right here. How do I get those numbers? Well, I do a couple of mathematical arithmetic, of course. So I can take 29.6, my point estimate, minus 2.1. What this would give me is 27.5, which is exactly what I have here. But then I can also take 29.6 and then plus 2.1. And this would give me 31.7, which is exactly what I have here. So I can use this information, a random margin of error, which we will find in a little bit, and then I can add and subtract from the point estimate what I found it to be. I can add and subtract that margin of error from the point estimate to give me bounds. Now, the reason why they're parentheses is because if you remember from algebra 2 specifically, we would call this interval notation. The reason why it's interval notation is because I can write this as 27.5, comma, and then 31.7. This technically is what we call my confidence interval. Sort of, kind of, sort of. Just roughly, my interval estimates. All right, but this is sort of what we're going to be doing today, kind of constructing these intervals over and over and over and over again so that we can see how confident we are that our sample does lie somewhere perhaps within the mean, okay, with the population mean. So let's move on. So the level of confidence, how does this level of confidence, this confidence interval kind of relate then to what we're learning, the interval estimate? Well, the definition, the level of confidence and the margin of error. So the level of confidence C is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. It keeps going over and over and over and over again. Okay, so you know from last week from the central limit theorem that when n is greater than or equal to 30, the sampling distribution of the sample means is, of course, a normal distribution. So even if we don't know the stuff for, even if we don't know anything for the even if we don't know the population parameters and whether or not it's normally distributed, as long as our sample n is greater than 30, then it will approximate a normal curve. Okay, that then after that, the level of confidence C is the area under the standard normal curve. And these are what we call the critical values, the z-scores, essentially. Those are like my critical value or z-scores. Okay? So let's continue on. So what if I'm given this graph? Okay, and this is what you'll see over and over and over again with the standardized normal distribution with z-scores that you don't know down here. Okay, you just don't know them. In order to find this little area, though, I can take 1/2 and then times 1 minus c. We did a little bit of this not last week, but the week before with 5.3. Now this c is your actual confidence level, your C level. So let's just say my C level, my level of confidence is 0.90, so 90%. That's the area in blue. Now my area in the yellow regions is the 1 minus C, so the 10%. So that's 10% altogether. Okay. If I want to know the area in each individual tail, I just take that 10% and do 1/2, which is 0.05. Okay, so that way it all equals 100 or 1. Now, if I want to find the critical value separating the left tail, all I have to do is what we call the inverse. So I need to find the inverse property of the z-score. So finding my z-score, that's 5.3 stuff. So we would use Desmos for this and use the inverse calculator. I'm going to show you that in a bit, but that's what we would use. Okay, this technically is already stuff we sort of already know, but we just are kind of adding what we call the level of confidence here. So take that in consideration, and let's move on. So the difference between the point estimate and then the actual parameter value of the population is called what we call the sampling error. So when it is estimated, the sampling error is the difference where my mean population for a population mean mu where the standard deviation is known. Let's start over. So for a population mean mu where the standard deviation, the population standard deviation is known, the margin of error is this. Okay, E equals, and I'm going to give you this formula, E equals my z-score, or my what we call sometimes the critical value, times the standard deviation of my sample means equals the z-score, or my critical values, times, and then we can go a little bit further and say this formula. Okay, so this formula right here. So this is the margin of error for mu. Okay, so this is the margin of error for mu, where our population standard deviation is known. Tomorrow, what we're going to be going through is what happens if I don't know whether or not the population standard deviation is known. Now, the population must be normally distributed, and we oftentimes will assume that to be the case. So if it's, we'll oftentimes assume that the population is normally distributed. It won't just tell us, it will just say assume it to be true. And then n must be greater than 30. Okay, our n must be somehow greater than 30. All right, let's go to town and let's start analyzing the margin of error by using the previous point estimates that I found in example 2. Sorry, in example 1. In example 1. Okay? So, in example 2, I have this first part. So we're going to use the data from example 1.1 and a 95% confidence level to find the margin of error for the mean number of hours worked by grocery store employees. So we want to assume that the population standard deviation is 7.9. Okay? So how do I do that? Well, before we get to Desmos, I'm going to show you how to get to Desmos. But before we do that, let's start calculating a couple things out, like my variables. What is my n? Well, in example 1.1, we said my n was 40. We also said right here that I want to assume my standard deviation is 7.9. So let's assume that it's 7.9. Okay. Notice how that's known. I'm knowing it to be the case. Okay. Now I want to find also my critical value, my z-score value. How do I solve for that? Well, I do need to use that knowledge from 5.3 in doing my inverse z-score properties. How do I do that? I'm going to show you right now. So give me 1 second. Come on. Oh my gosh. Get over there. What is even happening? Oh my gosh. I'm going to just, this is really upsetting. It's being really slow. Finally. Jeez. Give it a second to load. My goodness. Okay. Fantastic. So what do? Notice this is my Desmos calculator. This thing that you can use is on Google Classroom. I'm not going to show you that right now, but it's on Google Classroom Desmos links underneath the stats page. So please go there. You're going to click on 6.1 because that's the one that we're on right now. And once you click on 6.1, you're going to see a whole list of stuff. So I'm going to explain each one of these is what it is. Okay, so don't freak out. It is, I'm going to explain it, so just relax. Okay, so just relax. What these are different values, and I've labeled each one of what it is. So I've labeled this first part as critical values and then confidence intervals. Okay, basically the critical values and the confidence intervals. So my C equals what we call the confidence level. So this is the confidence level. All right. I do want a 95% confidence level. So 0.95, good deal. Okay. My capital C is what we call the critical value, and that's going to give me what I really want, my z-score value. Okay. Oftentimes we call the z-score the critical value as well. So if I want to find that critical value, I use my Desmos calculator. Now, the only thing that you are going to be changing is this right here, the 0.95. You're not going to change any of this, and you're not going to change anything else. You're only changing the things that have sliders in them. So for instance, this, it's already 0.95, which means your critical value is right here. Okay, that's all you need to know. That's your critical value. Make sense? Awesome. So that is your critical value, and that's what you're going to be using. So once I have that, so the only number that we need is that z-score critical value number, and that is located right here. That's the only number that we need. So when it asks you z sub c, that's what we need. Z sub c can easily be written as this. So z sub, what's my confidence level? It's 0.95. So I can write it like that as well. And what that is 1.96. That is my critical value at my confidence level of C equals 0.95. Okay? That's not my answer though. That's just my critical value. Okay, so this is technically my first step. My second step is to actually find my margin of error. So my margin of error is equal to my critical value of whatever my C level is times the population standard deviation all over the square root of n. So this is how I find my margin of error. Okay, so I already now found my critical value, which is 1.96. So I'm going to put that in right here, substitute that in, times, now what did we find for the population standard deviation? It is 7.9. So we found it was 7.9. And this is all over the square root of our sample size, which hasn't changed, and that's 40. When I plug this into the calculator, I get 2.4. So this is my E, my margin of error. So not too terrible, right? I'm going to explain all of this later. Okay, I'm going to explain all of this in a little bit. But technically, yes, you could find your margin of error on the calculator, and I'll explain that as we kind of move on in a bit. Okay, so probably after the next example, I'm going to go back and explain that. Okay, so what if we have this question? So what if we have this question? I'm going to erase this. I'm going to keep the 2.4 though. So the 2.4, I'm going to rewrite that. So this does equal 2.4. So use the data now in example 1.2 and then a 95% confidence level to find the margin of error for the mean number of workers. And assume that the standard deviation is 7.9 as well. Okay, so what do I do here? So I need to first list out all my different variables. So now I know my z-score of 0.95, my C level 0.95, my critical value is still 1.96. That has not changed. That's still going to be the same. Okay. My n though has changed, and that's going to be 30. And then my standard deviation hasn't changed. That's just going to be 7.9. I put all of these together and I plug them into my formula, my margin of error formula. So E equals my critical value 1.96 and then times 7.9 all over the square root of 30. What this equals is 2.83. Okay, 2.83. That's my margin of error. Now notice when I had a smaller sample size, my margin of error increased. When I had a smaller sample size, my margin of error increased. Okay, and that should not be any surprise because the closer you get in the population of numbers to your actual population of numbers, the closer, the more numbers you have in your sample, the closer you will be to the population, which means your margin of error is going to dwindle down because it's going to be closer to your actual answer. Okay, it's just going to dwindle down a little bit. It's not going to be as big of a margin. All right, so that's how you find the margin of error. I'm going to show you now how to use it quickly on Desmos. How to use the margin of error on Desmos. Let's go to the first one. If I scroll down, it tells you now your margin of error calculator, where n is your sample size, s is your population standard deviation, and then, of course, your z sub c is your z-score, or what we call your critical value. So what's my S? Well, my S was 7.9. So I'm actually going to go over here and I'm going to change this to 7.9. That's how my margin of error is changing. And then, of course, I'm going to look at my N and I'm going to change that to 40. Now it's already 40, which means, boom, I have 2.4. Now notice how that is exactly what I got. So you can use this calculator even to calculate your margin of error. Okay. Now, if I go to the second one, it's still 1.6, so that doesn't change, but my N does change. My standard deviation doesn't change, but my N changes. So let's change that to 30, and notice now I have 2.83, 2.826, which the 6 rounds to 2 to the 3. So again, use your margin of error calculator here because we're going to be using it a lot. All right, let's move on though to now, since we found the point estimate, we know how to do that. We know what confidence levels are. We know what interval estimates are, and we know what margin of errors are. Let's combine all of this together and construct what we call the confidence interval. Let's put all of it together to use what we call and construct the confidence interval. So what is the confidence interval for the population mean? So the C confidence interval for population mean, mu, is the following. So let me write that for you. It is this. Ready? So it is my sample mean minus my margin of error. And that means my population mean will be between that interval and my other number, which is my sample mean plus my margin of error. So this is what the confidence interval will be, okay? My sample mean minus my margin of error, and it's going to be in between that and my sample mean plus my margin of error. So the probability that the confidence interval contains is C. So the contains mu is C, assuming that the estimation process is, again, repeated for a large number of times, okay? So again, the probability that the confidence interval contains my population mean is that confidence level, so 95% confidence, assuming that the estimation process is repeated a large number of times, and so that it will roughly be that number, that probability. So let's erase and then move on. So here I'm going to go through a couple of guidelines. And these guidelines are going to be very, very beneficial to us as we kind of construct these. So first, you want to verify that, that the standard deviation is known. As I said, oftentimes it's very rare that this standard deviation is actually known for the population, but you're still going to try to verify it. And if it's given to you, then you're going to use 6.2 math, this tab on Desmos, 6.1 math, this tab on Desmos, the 6.1, okay, 6.1. You're going to be utilizing that if the standard deviation of the population is known. Okay, the sample is either random and either the population is normally distributed or n is greater than 30. If all of those things are true, then you can perform what we call the population confidence level interval. So find the sample statistics for n, and then that's supposed to be x bar, but that's okay. It's just x bar. So that means find your sample mean and then find what your sample size is. Okay? So I can write that out. So find the sample statistics. So basically, remember your x bar right here, that equals adding them all up, and then this is x, and then divided by n. So just remember that formula. Okay? Find the critical value. See, that's how you use Desmos. Okay, using this area right here, this z-score, this gives you your critical value there. You're going to be using Desmos to find that. And then find the margin of error. Remember, my margin of error equals my z-score, or my critical value, times the population standard deviation all over the square root of my sample size n. Okay? So that's the fourth step. And then the fifth step is find the left and right endpoints by adding and subtracting and form the confidence interval. So what is the left endpoint? So I'm going to say this is the left endpoint here. The left endpoint is x bar minus my margin of error. My right endpoint, that's going to be x bar plus my margin of error. So what together, all together, what is my interval? How do I find my interval? Well, that's going to be my confidence level, okay, or my confidence interval, what I just literally wrote on the last slide. And that's going to be your x bar, which is your sample mean, minus my margin of error. And your population mean is going to be in between that and your sample mean plus your margin of error. So that is the definition of a confidence interval, and that is exactly what you're going to be finding. So we're going to do the first couple ones by hand, probably just the first two by hand, and then the rest we're going to be doing using Desmos. Okay? So let's erase. So construct confidence levels or confidence intervals. So use the data from example 1.1 to construct a 95% confidence interval for the mean number of hours worked by grocery store employees. So let's go to town on this. The first thing that I'm going to do is list out my variables. This is pretty much going to be my very first step. My x bar, what we got was 29.6 there. Okay, and we also found in example 2.1 that my margin of error was 2.4. So this was 1.1, 29.6. We found this, my margin of error, to be 2.4 in example 2.1. Now, let's use this information to construct my intervals. So I'm going to first do my left endpoint. My left endpoint was my x bar minus my margin of error. So my x bar is 29.6 minus 2.4, and this is going to be equal to 27.2. So this is my left endpoint. Okay. Second, my right endpoint. How do I find my right endpoint? That's going to be my x bar, my sample mean, plus my margin of error. So my x bar was 29.6 plus 2.4. When I add those two together, I actually get 32 exactly. So that is my right endpoint. My third and final step is to kind of build this. What will this actually look like? If I put this on a number line, what this look like would be as follows. This would be 27, sorry. This would be 27.2, so 27.2. In the middle would be my point estimate, 29.6, okay, or my x bar. And then my right endpoint would be 32.0. So what this will look like is this in parentheses, because it's an interval and it's not included. It's no brackets or anything. It's no less than or greater than or equal to. Okay, it's just less than or greater than. And this right here, in between each of these, is what I call the margin of error. So in between each of that is what I call the margin of error. And of course, this is in between that is your mu, your population point estimate mean. Okay? So that's basically how to construct it by hand. All right? So let's go through one more example, and then we'll construct that one by hand, and then the rest will be just straight up using Desmos all together, okay? So let's see if you can, let's erase this. Let's see if you can solve this one by yourself. So go ahead, solve this one by yourself. Use the data from example 1.2. So let's actually, before you do that, let's just list them out. So what was your X bar? And then what was your mean? Or sorry, your margin of error. So your X bar here was 39.5. We got that from example 1.2. And then from example 2.2, what we got from my margin of error was 2.8. So use this to find your left endpoint, and then to find your right endpoint, and then see if you can graph it as well. So go ahead, pause the video, and see where you get. Boom. So this is what I have. So my left endpoint was 36.7, my right endpoint was 42.3, and this is my graph. So what this says is I can be 95% confident that the mean number of hours worked by grocery store employees is between 36.7 to 42.3. Okay, given that my point estimate or my sample mean was 39.5 and my margin of error was 2.8. Pretty exciting, right? I think it's rather very, very exciting. Okay, so now let's erase this and say goodbye to solving these by hand, and let's start just hashing these out using Desmos. Hashing these out using Desmos, and we're going to be using Desmos a lot. So we're going to be now using the data from example 1.1. So now use the data from example 1.1 to construct a 99% confidence interval for the mean number of hours worked by grocery store employees. Okay, so what do I do? That's the first thing I want to ask. So let's start listing out all my variables once again. So my X bar, if I'm going to use example 1.1, what is my X bar? We said that was 29.6. Okay, my N, that was 40. All right. My population standard deviation, we said that was 7.9. Okay, in the previous examples, we said assume it to be 7.9. All right. And then my sample standard deviation, we got to be 7.9 all over the square root of 40. And we said that equals 1.25. Okay. If we didn't already calculate that before, then I'm calculating it now. So I'm calculating that now right here. My sample standard deviation is 7.9 all over 40 because that was how many were in my sample size for example 1.1 was 40. I calculate that real quick and I get 1.25. Now, what do I do? How do I solve this? And how could I solve this using just my confidence level interval calculator? Are you ready? So this now is going to just be straight up Desmos. So let's get to it. What is my actual answer? Let's go over here to find out. First of all, I don't want a 95% confidence interval. I want to change my confidence level to be not 95, but 99. Okay, that's the first part. I then go down. Notice how my Z, my critical value, has changed, but that's okay. It's not asking us for the critical value. So I scroll down. Notice how my margin of error has also changed. That's okay. It's not asking us what the margin of error is. It's asking us what the confidence level is. Now, the one thing, though, that I do need to change is my standard deviation and my sample size if I haven't already. Now, notice my standard deviation of the population. I don't need to change. That's still 7.9. So I'm still solid on that. But I do need to change this. It's definitely not 30. It's 40. Okay? 40. So then I scroll down. And now what I want to do is change my X bar, my sample mean. It's definitely not 144, right? We said my sample mean was 29.6. So I'm going to erase this, and we're going to write 29.6. And now what we can clearly see is my two intervals. What does that mean? This means these are my answers. I'm done. So that's how you use the full power of the Desmos calculator. So let's go back over here and let's actually write this out. So that means in parentheses, I have my left endpoint, 26.4, comma, and then 32.8. This is my confidence level, and this is my answer. And oftentimes you will write it like this into Math Excel. This says I can be 99% confidence that my population mean lies in between the number of hours worked, the mean number of hours worked from 26.4 to 32.8. My population mean will more than likely lie somewhere in between there, and I'm 99% confident that it can be like that. That's pretty cool, right? I think that's pretty solid that we can just type some stuff in a calculator and it just calculates all that for us. That's amazing. Okay, so let's try another one. So let's erase this and let's get one that's completely just brand new, just completely different. Ready? So construct a 90% confidence and a 99% confidence interval for the population mean, okay? A publisher wants to estimate the mean length of time in minutes for all adults spending reading newspapers. All adults spend reading newspapers. To determine this estimate, the publisher takes a random sample of 15 people. So automatically, what this tells me is my N is 15, okay? All right. The publisher assumes that my standard deviation is going to be 2.2 minutes. That's going to be my standard deviation. So my standard deviation is 2.2. Okay, so I'm going to write that right here. Okay, and if we continue reading, and the population of times is, of course, normally distributed. So I have a lot of things that I need to kind of calculate here. All right. So what are the things that I need to calculate? Well, first of all, I'm given this information. So actually, let me erase all this and let me rewrite it. All right, so I just rewrote it off to the side. Again, my sample size is 15 right here, and then my standard deviation is 2.2. Now, I want to find my sample standard deviation as well. Just in case, I want to find my sample standard deviation as well, so I can actually plug that in. Okay, so what's my sample standard deviation? My sample standard deviation right here, just in case they ask for it. I don't think you don't necessarily need it to find your interval, but they may ask for it anyways. So I'm going to take 2.2 divided by the square root of 15. And what that will equal is 0.57. So again, I like to find the sample standard deviation just in case they ask for it, just in case. And also because if they ask for the margin of error, you can use that, even though it does calculate it for you. Okay, so now what I also want to find is a couple more variables, specifically my x-bar. Like, what the junk is my x-bar? When you're given something like this, you do have to calculate that by hand. Okay, most of the time they do give you the x-bar, but in this case, you do have to calculate by hand. So add up all the numbers, divide by the number of numbers. What you should get is that your x-bar is 8.5. When you add up all the numbers and divide by the number of numbers, you should get 8.5. Now, there will be 15 people. These are 15 numbers. So add them all up, divide by 15, you'll get 8.5. Now, that I have all of this information, I'm now going to go over here and start doing my confidence level. Okay? So let's scroll all the way back up. I do want 90 to start with. Now, notice I'm only doing 90 first. So I want both 90 and 99. So let's do 90 first. And I'm just going to write that over here off to the side, actually. Let's do, first, let's do 90% confidence. And then down here, we'll do 99% confidence. Okay? So let's do the first one, 90%. Okay, see how my z-score, my critical value changes? Sometimes they will be asking for that critical value, so just make sure you know it's there. Of course, my margin of error will change as well, but I do need to change my my population standard deviation. It's not 7.9, but 7.2. And then my sample size has changed to be 15. Okay. Now, this is, of course, not greater than 30, but that's okay because the population is normally distributed, and they tell us that right here. So it's okay if it's not greater than 30. Last thing I need to change is my mean that I found right here. It's not 29.6, it's 8.5. Okay, it's 8.5. And this is going to be my my left and right endpoints. So let's go and put that in. So that means I'm going to look at this for my left, and I'm going to round that to, let's just say 7.56, roughly, maybe 7.57. So I have 7.57, comma, and then right here I have 9.43. So 9.43. So that right there is my confidence level for 90%. That right there is my confidence level for 90%. Okay? So that's my left endpoint. That's my right endpoint. That's my answer. That's my confidence level. I can be 90% sure that my population mean lies between those two numbers. All right? Now, let's go and change a couple things. The only thing we need to change for 99% is the very, very top. Okay, so instead of 90, we need to change that to 99. Everything else will stay the same. My standard deviation, my sample size, all of that, even my mean, 8.5, all of that will stay the same. So now let's go back and find out what this is. This right here is looks like 7.04. And then this is 9.96. Okay, 9.96. And that is my confidence level for 99%. Now notice my margin of error is a little bit wider, meaning it's a little bit bigger, because the more confident you are, the more you kind of have to give room for error here. Like, you don't really know, right? So that's why these are bigger intervals. And be careful, because on Math Excel, it's actually going to ask that. It's going to ask you, what kind of intervals are there? Like, what is the relationship between 90% and 99? The higher you go in intervals, the higher you have for a confidence interval, the fatter your interval will be. Because it's basically strict. You need to be more confident, and so you have to give yourself more wiggle room, okay? Instead of less wiggle room like this. Okay, so let's erase that, and let's move on to a couple more examples. So example 5. Example 5, a college admissions director wishes to estimate the mean age of all students currently enrolled in a random sample of 20 students. So automatically, I can say a random sample of 20 students. I'm going to write this off to the side. N equals 20. So I know it's a random sample of 20 students. The mean age is found to be 22.9. Okay, so 22.9 is the mean age. So I'm going to write that to be this. So 22.9 is my mean age. That's nice. I didn't need to solve it out at all. They gave it to me. The standard deviation is also known, which means we're going to be using 6.1 because I know the standard deviation to be my population standard deviation to be 1.5. Okay, so that means my population standard deviation is 1.5. It is known. Okay, now I could find my sample standard deviation here. I'm not going to, but I could find it in case it wanted to ask for that. All right, so now I'm just going to understand that I need a 90% confidence level. So I'm going to go over here and start plugging stuff in. Let's go all the way back to the top. I don't want 99, I want 90. I'm going to scroll down, and I want to change my sample, I do want to change my sample size, but I also want to change my population standard deviation. Population standard deviation, we said, was 1.5. And then the sample size finally is going to be 20. Now I do go down more because I need to change what I call the sample mean, my x1 here. What is my sample mean? My sample mean, they give it to us, it's 22.9. So I'm going to change that 22.9 and then voila, they give you your interval. So what is that interval? What is my C interval here? My C interval for 90% is 22, just looking at my left endpoint. So 22.34, comma, 22.34, comma, 23.45. Let's just round to 2 decimal places here. So 45. And this is my answer. Pretty nifty, right? I think it's pretty nifty. Okay, really, you're just plugging into decimals. That's all you're doing. Okay, that's my confidence interval for 90 degrees. And I can be confident, 90% confident, that my population mean will fall between those ages. Okay, sweet. Let's erase this and then move on to my next example. Now, construct a 90% confidence interval of the population mean age for college students of example 5.1 with a sample size increased to 30 students. Okay, so now it's not going to be 15, or sorry, it's not going to be 20 students, it's going to be 30. So now let's do that. Let's change it to 30. Now everything else is going to be the same. So my mean is still 22.9. And then my standard deviation is still 1.5. The only thing that's really changed here is not even my C level. My C level really hasn't changed at all either. Everything else is changing except for the fact I'm switching my sample size to 30. Okay, so I'm going to go over here and switch my sample size to 30, but everything else is going to stay the same. So now, what are my confidence level interval? What's my confidence intervals? So that is 22.45, comma, 23.35. What is happening here? Okay. So comma, and then this is 23.35. So that is my confidence interval. Now compare it with your answer. Well, as I said, the more you increase the sample size, if you increase the sample size, then that means you'll get a smaller margin of error. So right here in this second one, since we increase the sample size, we will get a smaller margin of error. What does that mean? That means we're going to be closer to the population, which means we don't need as much wiggle room in my margin, my interval. Okay? Just like if I decrease my confidence interval, I also will have a smaller margin of error because I don't need as much wiggle room. But if I increase my confidence level to 90%, from 90% to like 99%, then that means it's going to be a little bit harder to construct, which means I need to restrict my, which means I need to expand my margin of error there. Okay, so let's erase that and go on to what we call the minimum sample size. So the minimum sample size is actually very, very simple, guys. I'm just going to go through two real quick examples. Very, very simple indeed. And I'm actually going to utilize Desmos for it a little bit, just probably the blank ones down here. So given a C confidence level and a margin of error E, the minimum sample size N needed to estimate the population mean mu is this, is what follows. So it's N equals my Z-score times my population standard deviation all over my margin of error and then squared. Okay, this right here, this formula is very, very nifty, and it will allow us to just really, really quick just calculate everything that I need to calculate. Okay, cool. Cool. So when this is unknown, when your sigma is unknown, your population standard deviation is unknown, you can estimate it by using what we call S. Okay, provided that you have a preliminary sample with at least 30 members. Okay, so let's erase this. I'm going to show you what that means in a bit. So this example is wanting us to determine the minimum sample size. So an economics researcher in example 1 wants to estimate the mean number of hours worked by all grocery store employees in the county. Now, how many employees must be included in the sample to be 95% confident? So now notice how we're kind of working backwards here. 95% confident that the sample mean is within 1.5 hours of the population mean. So the first thing I need to do is kind of list out my variables. My C level is 0.95. My Z-score of 0.95 of my C level is 1.96. So you can calculate that using Desmos real quick, or you can just know we've done 95% confidence level before. And my critical value, my Z-score at that level was always 1.96. My standard deviation, my population standard deviation was 7.9. So this is the population standard deviation that I'm kind of using throughout the whole lesson here. We also found my margin of error is 1.5. Mainly, they told me that what if it's 1.5 is within 1.5 hours. So that is my margin of error right there. My second step is to use my formula and start plugging everything in. So n equals, I'm going to do 1.96 times 7.9 all over my 1.5 for my margin of error, and now I want to square that. So let's go over here and do that real quick. I'm going to show you how to type that into the calculator. So I have 1.96 and times, I have 7.9 all over 1.5. And I want to square this. Sorry, I want to square this to be as such. So what does that tell me? This tells me my mean, my minimum sample size, 106.56. Okay, so roughly my minimum sample size is 107 employees. So 107 employees. Now, why do I round? Because again, you have 106.5, and to get the minimum, I need to get the top value. So it's 107 employees, 107 employees. That is my minimum sample size. Okay, so not too bad, right? You just need to kind of plug some stuff in, and then it will solve it for you. So I'm going to do this last one and have you actually do it by yourself. Okay, so let's list out all the things that we need to do, and then let's see if you can plug it in yourself. My C level is 0.95. That's what they say. My Z-score at that C level is 1.96, just like the problem before. My standard deviation is still 7.9 because I'm going to compare it with example 6, so I'm still using the exact same thing. But now my margin of error is a little bit different. My margin of error is now 2. So go ahead and try to figure out your answer. What would be my minimum sample size? And you're going to see me change this, and then you're going to see that pop up on the screen. So go ahead, pause the video, see if you can try it. Perfect. So all I have to do is just change that E there from 1.5 to 2, and then I get 59.9 which would be roughly 60 employees. So in order to achieve a 95% confidence that my mean lies between any given interval, that means I need to have a minimum sample of 60 employees. Okay, pretty cool. Let's erase and let's actually summarize the lesson. So what did we learn? We learned actually a lot of things today. We learned the point estimate and the margin of error. We also learned how to construct and interpret confidence intervals for a population mean when the standard deviation is in fact known for the population. We also determine the minimum sample size required when estimating a population mean. So if you have any questions on the homework, guys, please let me know. Please, please, please. I know this was a pretty long video, but it's probably going to be helpful, and I guarantee it. Tomorrow and the next day are almost exactly identical to this. It's just a little bit different when we calculate it using Desmos, but we're going to be using pretty much the exact same calculator. So I'm going to go a little bit faster on those videos so it won't be as long. But until then, make good choices, do your homework. See you guys later.